Build a tiny Softmax classifier in plain Python. By the end, you will have a working forward pass, a probability output that adds to 1, and a tiny baseline accuracy for a toy dataset. You will see how logits turn into probabilities, how argmax picks a class, and how a temperature parameter sharpens or softens confidence. I'm Professor Pi, teaching AI foundations with Python from basics to advanced. Softmax matters because it gives calibrated probabilities. We usually train Softmax models by minimizing cross-entropy, which measures how far the predicted probability distribution is from the true labels. The trade-off is simplicity versus capacity. A tiny linear Softmax is fast and interpretable, but it will not match a deep network on complex data. Practically, it is perfect for small datasets, debug experiments, and understanding probability outputs before you scale up. Think of Softmax as a polite competition among class scores. Each class proposes a number called a logit, and Softmax turns those numbers into a single probability spread across classes. It shines when you want probabilities rather than just labels, and it fails when the decision boundary is nonlinear and complex. We will build a minimal pipeline so you can see every step and then think about training. We will build a tiny dataset, compute raw class scores, convert them to probabilities, measure a baseline accuracy, and play with a temperature parameter to change confidence before finally producing a full prediction table. Now we create toy data and compute linear logits for a single example. This snippet builds toy data and computes linear logits for one sample. It creates a tiny input matrix X and a matching label list Y, plus a weight matrix W and a bias vector B for 3 classes. The code picks the first sample X0, so we can track a single forward pass clearly. The list Z0 holds the class scores produced by taking the dot product between X0 and each class vector from W, and then adding the corresponding bias from B. These unnormalized numbers are called logits because they are fed to Softmax next. The printed values show raw class evidence before probability conversion, which sets up the next step. Next, we'll stabilize and convert those logits into probabilities. This snippet turns logits into stable Softmax probabilities for one sample. It recomputes Z0, the 3 class logits for the first example, and then applies a numeric trick to prevent overflow by subtracting the maximum logit before exponentiating. Each exponentiated, shifted logit becomes an unnormalized score. The list P divides each unnormalized score by the sum, so the 3 entries add to 1 and form a probability distribution. The code rounds values to 2 decimals, so the output is compact, but faithful to the model belief about each class. The printed list shows the model's probability over classes for that input. Next, we will predict labels for the whole tiny dataset and check baseline accuracy. This snippet ranks classes with argmax and computes dataset accuracy. For each input row in X, it collects a vector of logits by summing feature times weight for every class, and then adding the class bias. The predictions vector picks the index of the largest score in each logit vector, which is argmax, the position of the top score. Accuracy is computed as the fraction of predicted labels that match the true labels Y. The snippet counts matches, divides by the number of samples, and rounds the result for readability. The printed value is the current accuracy of this untrained Softmax baseline on the toy set. Next, we will inspect how temperature changes the model's confidence. This snippet applies temperature scaling to show confidence sharpening versus smoothing. It recomputes Z0 for the same input and then normalizes differences by subtracting the top score, so we work with gaps. Instead of converting the whole vector, the code computes the top class probability directly by taking 1 over 1 plus the sum of exponentials of the non-top gaps divided by the temperature. Using a temperature of 0.5 magnifies gaps and sharpens the top probability. while a temperature of 2 shrinks gaps and spreads probability mass more evenly. Changing temperature higher softens confidence, and lowering it concentrates mass on the highest logit. The printed pair reveals how confidence shifts with temperature. Finally, we will produce batch Softmax predictions for every sample. This snippet produces batch Softmax predictions for the entire dataset. It builds a list Z of logits where each entry is the per-class scores for a sample, computed by summing feature times weight per class and then adding the class bias. For every logit vector in Z, the code shifts by the maximum and exponentiates to keep numbers stable. Each list of exponentials is normalized by its sum, so every inner list becomes a probability distribution that sums to 1. The probabilities are rounded to 2 decimals to keep the table readable. The printed list of lists is a full baseline prediction table for the tiny dataset. Recap: it is a minimal, linear softmax that converts logits to probabilities and produces predictions. Use it to inspect model confidence, debug label issues, or teach probability outputs. One caveat is that this linear baseline cannot capture complex nonlinear patterns without feature engineering or a more powerful model. Next step: train the weight matrix and bias with gradient descent on cross-entropy for more realistic improvements. Track training accuracy over a larger toy corpus and compare learning curves to see real gains. If clear AI foundations in Python help you learn faster, subscribe and watch the AI Foundations videos.